When the primary winding connection of a transformer differs from the secondary, several effects on its operation can occur. Firstly, the phase shift between the primary and secondary voltages and currents will change. For example, if the primary connection is changed from Dyn7 to Dyn5, the phase shift will change by 30 degrees. Secondly, the voltage and current ratios between the primary and secondary will also change. This is because the winding connections affect the effective turns ratio of the transformer. Thirdly, the power factor of the transformer can be affected, as the phase relationship between the voltages and currents changes. Dyn5 winding connection has a leading power factor, while Dyn7 winding connection has a lagging power factor. The overall performance of the transformer may be impacted, including its efficiency, regulation, and transient response. Different winding connections can result in different levels of stray losses and harmonics. Specifically, for a change from Dyn7 to Dyn5 in the primary, the phase shift between primary and secondary voltages will decrease by 30 degrees. The voltage ratio will decrease slightly, while the current ratio will increase slightly. The power factor will become more leading. The transformer regulation and efficiency may slightly decrease. It's important to ensure that the primary and secondary winding connections are compatible and match the intended application. Changing the winding connections can have significant effects on the transformer's operation and must be done carefully and by a qualified technician. Transformers are essential components in electrical power systems, responsible for stepping up or stepping down voltage levels to efficiently transmit and distribute electrical energy. Understanding the intricacies of transformer operation, including the effects of different winding connections, is crucial for engineers and technicians involved in power system design, operation, and maintenance. The winding connection, often represented by symbols like Dyn5 or Dyn7, describes the configuration of the primary and secondary windings of a three-phase transformer and the resulting phase shift between the voltages on the two sides. These connections significantly influence the transformer's performance characteristics and its compatibility with various load types and system configurations. When the primary and secondary winding connections of a transformer differ, it can lead to several notable effects. These effects encompass changes in phase shift voltage and current ratios, power factor, and overall transformer performance. Let's delve into each of these effects in more detail. Firstly, the phase shift between the primary and secondary voltages and currents is directly influenced by the transformer's winding connection. Different winding configurations introduce different phase displacements between the voltages on the primary and secondary sides. For instance, changing the primary connection from Dyn7 to Dyn5 results in a 30-degree change in the phase shift. This phase shift is crucial in three-phase systems because it determines how the voltages and currents from different transformers interact when connected in parallel or when supplying unbalanced loads. Understanding and managing the phase shift is essential for ensuring proper system operation and preventing circulating currents. Secondly, the voltage and current ratios between the primary and secondary sides of the transformer are also affected by the winding connections. The effective turns ratio of the transformer, which determines the voltage and current transformation, depends on the winding configuration. Different connections can alter the turns ratio, leading to variations in the output voltage and current for a given input. This is particularly important when matching the transformer's output voltage to the voltage requirements of the connected loads. Thirdly, the power factor of the transformer can be significantly impacted by the winding connection. The phase relationship between the voltages and currents determines the power factor, which is a measure of how effectively electrical power is being used. A Dyn5 winding connection typically exhibits a leading power factor, while a Dyn7 connection tends to have a lagging power factor. These differences in power factor can affect the overall power system's stability and efficiency. It's crucial to choose the appropriate winding connection to maintain a power factor close to unity, minimizing losses and maximizing system performance. Finally, the overall performance of the transformer, including its efficiency, regulation, and transient response, can be influenced by the winding connection. Different connections can result in varying levels of stray losses, which are energy losses due to magnetic fields outside the core. and harmonics, which are unwanted frequencies in the voltage and current waveforms. These factors can impact the transformer's ability to efficiently transfer power and maintain a stable output voltage under varying load conditions. Specifically, when changing the primary connection from Dyn7 to Dyn5, several changes occur. The phase shift between the primary and secondary voltages decreases by 30 degrees. The voltage ratio decreases slightly, while the current ratio increases slightly. The power factor becomes more leading, which can be beneficial in some applications. However, the transformer's regulation and efficiency may slightly decrease due to increased losses. It's essential to carefully consider these trade-offs when selecting or modifying the winding connections. It's important to emphasize that the primary and secondary winding connections must be compatible and aligned with the intended application. Incompatible connections can lead to significant operational issues, including voltage imbalances, circulating currents, and reduced efficiency. Modifying winding connections requires careful planning and execution by a qualified technician. It's not a task to be undertaken lightly, as it can have far-reaching consequences for the entire power system. When selecting a transformer for a specific application, engineers must carefully consider the required voltage transformation, phase shift, and power factor characteristics. The winding connection is a crucial factor in meeting these requirements. For instance, in applications where parallel operation of transformers is necessary, the winding connections must be chosen to ensure that the phase shifts are compatible, preventing circulating currents between the transformers. In applications with unbalanced loads, certain winding connections may be preferred to minimize voltage imbalances on the secondary side. Understanding the nuances of different winding connections is essential for ensuring optimal performance and reliability. In summary, the winding connection of a transformer plays a critical role in determining its operating characteristics and its compatibility with various power system configurations. Changes in a winding connection can have significant effects on phase shift, voltage and current ratios, power factor, and overall transformer performance. It's essential to carefully select and maintain the appropriate winding connections to ensure efficient and reliable operation of the electrical power system. Choosing the right transformer involves a meticulous evaluation of the load requirements, system configuration, and desired performance characteristics. The winding connection is a key parameter that must be carefully considered to ensure compatibility and optimal operation. Consulting with experienced engineers and technicians is highly recommended when making decisions about transformer selection and winding connections. It is good to also ensure to consult the manufacturer's documentation and adhere to relevant industry standards. The winding connections impact many aspects of the power systems, including voltage regulation. Voltage regulation is the ability of a transformer to maintain a constant secondary voltage under varying load conditions. Different winding connections can affect the transformer's voltage regulation performance. For example, some connections may exhibit better voltage regulation under unbalanced load conditions than others. Therefore, it is good to consider the voltage regulation requirements of the application when selecting the winding connection. The winding connections also affect the harmonic distortion. Harmonics are unwanted frequencies in the voltage and current waveforms that can cause problems in electrical equipment. Some winding connections can help to reduce harmonic distortion, while others may exacerbate it. Therefore, understanding the harmonic characteristics of different winding connections is essential for mitigating harmonic-related issues. Understanding the temperature rise is also important. Transformers generate heat during operation due to core losses and winding losses. The winding connection can affect the temperature rise within the transformer. Some connections may result in higher temperature rises than others, potentially reducing the transformer's lifespan. It is important to consider the temperature rise limitations of the transformer when selecting the winding connection. The inrush current should be considered. When a transformer is energized, it can experience a large inrush current, which is a temporary surge of current that can stress the transformer and other equipment. The winding connection can affect the magnitude and duration of the inrush current. Some connections may exhibit higher inrush currents than others. Considering the inrush current characteristics of different winding connections can help to mitigate potential problems during transformer energization. Additionally, the transformer protection is critical. Transformers are typically protected by fuses, circuit breakers, or other protective devices. The winding connection can affect the performance of these protective devices. For example, some connections may require different types of protective devices or different settings. Understanding the interaction between the winding connection and the protection system is essential for ensuring adequate protection of the transformer. Also, the transformer impedance is an important value. The impedance of a transformer is a measure of its opposition to the flow of alternating current. The winding connection can affect the transformer's impedance. Some connections may have higher impedance than others, which can affect the transformer's ability to handle fault currents and maintain voltage stability. It's also good to consider the transformer grounding practices. The grounding of a transformer is essential for safety and protection. The winding connection can affect the grounding requirements of the transformer. Some connections may require different grounding schemes than others. Adhering to relevant grounding standards and best practices is crucial for ensuring a safe and reliable electrical system. Furthermore, the paralleling operation has some important notes. When transformers are connected in parallel, they must have compatible winding connections to ensure proper operation. Mismatched winding connections can lead to circulating currents and other problems. Understanding the paralleling requirements of different winding connections is essential for successful parallel operation. Considering the unbalanced load handling is also vital. Unbalanced loads can cause voltage imbalances and other problems in electrical systems. Some winding connections are better at handling unbalanced loads than others. Considering the expected load balance when selecting the winding connection can help to minimize voltage imbalances. Also, the transformer efficiency varies. The efficiency of a transformer is a measure of its ability to transfer power from the primary side to the secondary side. The winding connection can affect the transformer's efficiency. Some connections may be more efficient than others. It's important to consider the efficiency requirements of the application when selecting the winding connection. And also, the transformer reliability is important. The reliability of a transformer is its ability to operate without failure for an extended period. The winding connection can affect the transformer's reliability. Some connections may be more prone to failures than others. Considering the reliability implications of different winding connections can help to ensure a long and trouble-free service life. All in all, the selection and application of transformer winding connections require a thorough understanding of electrical engineering principles, power system design, and industry best practices. Consulting with experienced engineers and technicians is highly recommended to ensure that the chosen winding connection is appropriate for the specific application and meets the required performance and safety standards. It is also crucial to consult the transformer manufacturer's documentation and adhere to relevant industry standards. The winding connections also affect the core form versus shell form considerations. Transformers are available in two main core types, core form and shell form. The winding connection can affect the choice between these two core types. Core form transformers typically have the windings wrapped around the core, while shell form transformers have the core wrapped around the windings. The choice between core form and shell form depends on factors such as voltage level, current level, and desired performance characteristics. This is good to factor in when selecting the transformer. Consider the vector group as well. The vector group of a transformer specifies the phase relationship between the primary and secondary voltages. The vector group is determined by the winding connection. Common vector groups include Dyn11, Dyn5, YN-DON, and YN11. The choice of vector group depends on the specific application requirements. Also, think about the tap changers, as many transformers are equipped with tap changers, which allow the turns ratio to be adjusted. The winding connection can affect the location and type of tap changer that can be used. Tap changers can be located in the high voltage side or the low voltage side of the transformer. The choice of tap changer location depends on factors such as voltage level and current level. One of the considerations is the tertiary winding as well. Some transformers are equipped with a tertiary winding, which is an additional winding that provides a third voltage level. The winding connection can affect the configuration and application of the tertiary winding. Tertiary windings are often used for power factor correction, harmonic filtering, or supplying auxiliary loads. It's also good to understand the zigzag windings. Zigzag windings are a special type of winding connection that can be used to reduce harmonic currents and improve voltage balance. Zigzag windings are often used in transformers that supply unbalanced loads. Another important note is regarding autotransformers. Autotransformers are a type of transformer that uses a single winding for both the primary and secondary sides. Autotransformers are typically smaller and lighter than conventional transformers but do not provide electrical isolation between the primary and secondary sides. The winding connection in an autotransformer is different from that in a conventional transformer. One may also need to understand the buck-boost transformers. Buck-boost transformers are a type of transformer that can be used to increase or decrease the voltage by a small amount. Buck-boost transformers are often used to compensate for voltage drops in long power lines. The winding connection in a buck-boost transformer is different from that in a conventional transformer. Another term of the transformer is harmonics mitigation, which is an essential consideration. Harmonics are unwanted frequencies in the voltage and current waveforms that can cause problems in electrical equipment. Certain winding connections can help to mitigate harmonics, while others may exacerbate them. Understanding the harmonic characteristics of different winding connections is essential for mitigating harmonic-related issues. And finally, the transient voltage suppression is an important term. Transient voltages are short-duration voltage spikes that can damage electrical equipment. Certain winding connections can provide better transient voltage suppression than others. Considering the transient voltage environment in the application when selecting the winding connection can help to protect the equipment from damage.